Okay, so in the last class, we discussed about the operation of MOS transistor, and we also derived derived some charge equation. Um, so what we'll do today? So today, because see, today we'll do the exact solution of charge and potential in the MOS transistor. Uh, so uh, to to tell means if you look at the operation of MOS transistor, basically we are interested in the charges in the silicon, right? So uh, I have my metal, right, and here oxide and the semiconductor, right? So this is the silicon. So when you apply gate voltage, right, their charges are induced in the silicon, right? So I am more interested in those charges because once the charges are introduced, uh, so in the beginning the depletion charges are introduced, right? The charges which are immobile, right, and these charges are not moving. But as you go on increasing the increasing gate voltage, these immobile charges will increase, and it will increase the potential of the substrate. So if the potential of the substrate is increased, that means we are forward biasing this source to substrate and drain to substrate junctions. So once these junctions are forward biased, the electrons are injected from source and drain to the channel, and these electrons are mobile charges, right? So when you talk about current, when we will talk about current, so these mobile charges will only flow, right? So finally, we are interested in these mobile charges, right? But for these mobile charges, we also want to know how much depletion charges are needed to create those mobile charges, right? Okay, so we'll do this exact solution. So basically, we'll see the relation between charge and potential in the MOS transistor. When I talk about charge and potential, so this is basically charge and the potential in the silicon, right? Okay, so the charge in the silicon, if you see this, because the charge, this is my x direction, right? So this is my x direction, right? So your charge is varying in the x direction. So if you could write this total charge in the silicon, is this is a standard equation, right? So charges might be because of holes or electrons or positively charged donor ions or negative charged acceptor ions, right? So these are the four sources of charge, right? So if I write charge in the silicon is Q times Px minus Nx plus Nd plus minus Na minus, right? So last class we derived this Px. So basically the number of holes, right? So Px is because your psi, this psi here, right? So if you look at this psi here, so this is dependent on x, right? And psi varies, the potential varies from the silicon dioxide interface towards the body, right? Towards the body. So your P, the number of holes as a function of x is nothing but Na. Na is the number of holes in the beginning when there is no voltage applied, times e to the minus q psi s by kt, right? So we'll only have holes, more holes, if you apply negative Vg. That means if the potential is negative, right? So that's the reason if psi s is negative, your Px will increase, right? Okay. And Nx, this is my number of electrons. So this is the usual standard equation because the number of electrons injected from source to body or source to substrate is nothing but the number of electrons present earlier, Ni square by Na, times e to the q psi by kt, right? See, this is same as we are talking about the PN. So when we are discussing PN junction, right? So if I have a PN junction and I have um, okay, so I have Ni square by Nd number of holes here, right? So if I forward bias these junctions, so number of holes injected from P to N is nothing but Ni square by Nd times exponential your voltage across the junction divided by thermal voltage, right? So so here we are doing the same thing, right? So uh, the number of electrons injected from source to substrate is nothing but Ni square Na. This is the initial number of electrons Ni square by Na times exponential q psi by kt. Psi is the potential across the junction. Psi is the voltage across the junction. Voltage across the n plus p junctions, right? Okay. Um, so so this equation I wrote. So right. But if you look at um, the electric field, right? So electric field does not actually reach the substrate, right? If you look at this part here, right, this part very deep in the substrate, electric field does not reach here, right? So that region is basically charge neutral. That region stays charge neutral. So I could write this in that region 0, because charge neutral means total charge is 0. And if I have this equation, so q times Na. So this is number of holes. Number of holes is this is number of holes Na. Electron is Ni square by Na, and this is the ions, right? Acceptor ions and donor ions, right? So from this equation, I could write Nd plus minus Na minus is minus Na plus Ni square by Na, right? From this equation. Right, then if I put it, right, so now I know the P n Nd plus minus Na minus. If I put it in the same equation, so I will replace this Px by Na e to the minus q psi by kt, Nx by Ni square by Na e to the q psi by kt, q psi by kt, and then Nd plus minus Na minus is nothing but minus Na plus Ni square by Na, right? So this is, then I could simplify, and I could write it like this. So q times Na into e to the minus q psi by kt minus 1, and Ni square by Na times e to the q psi, e to the q psi by kt minus 1. Okay, so so this is my how the charge varies in the varies in the silicon, right? Then means if I want to means basically if I want to find electric field or potential, so basically we always start with the Gauss law, right? So means we know that del dot D equal to rho, or this equation we know, right? This is our Poisson's equation, right? Uh, so d square psi by dx square is minus rho by epsilon silicon, and so I could write here, so d square psi by dx square is minus q by epsilon. So this is the charge, right? So charge is nothing but q times this much. So means this equation is nothing but d square psi by dx square equal to minus total charge in the silicon divided by epsilon, right? Um, so right, so I could write this equation. Right. And then I have to solve for psi x, right? How the psi varies, right? So basically, so this is a simple um, uh, mathematical thing. So if you see d square psi by dx square, I could always write it by d by dx d psi by dx, and I could also write by d psi by dx into d psi by dx into 1 by d psi, right? So if I do that, then I could uh, means this equation here I could write like this, right? So in the right hand side and the left hand side, I have d psi by dx and differential of d psi by dx equal to charge into d psi, right? So then I have to integrate. If I integrate both the sides, right? If I integrate both the sides, so left hand side I'll integrate from 0 to d psi by dx, and the right hand side I'll integrate from 0 to psi. So if I do that, so this your left hand side will be half d psi by dx square. On the right hand side, you could integrate, right? So basically, you'll get this equation, right? So this is not very hard for you. So you could also find that, right? And the limits means basically you have to vary between 0 and psi. right? So if I put these conditions here, so finally you will get this equation, right? Finally you will get this equation here, right? So now, so your okay, so I have written here this equation again. So this is just the simplified version of this equation, right? Uh, so from here, if I want to find d psi by dx, so d psi by dx will be 2 times. So 2 will means uh, so if you multiply 2 in the left and right hand side and take the root over, so you'll get the d psi by dx, right? And d psi by dx, we know that this is the electric field, right? And we're talking about electric field in the silicon, right? And if you want to look at the surface electric field, right? So basically the electric field at the surface, right? So what I was talking about is this is my silicon, and um, right. So your Ex also varies with the silicon. I mean, it varies with X. Your electric field varies with X as you go from surface to the body to the bulk. But at X equal to 0, so this is my Es, that is at X equal to 0. Um, so I know that the surface, the potential is also psi s, the surface potential, and the surface potential is nothing but the potential drop across the silicon, right? So if I do that, then this will be then if I do Es, the your electric field at the surface, Es, right? So then you have to replace this psi by psi s, right? So you have to replace this psi by psi s, right? So this is the surface electric field, right? So why I'm interested in the surface electric field? Because if you see, um, this is your interface, right? So I have my gate here. This is my gate, right? I am giving a gate voltage. That means I have putting some positive charges. If I am applying positive voltage, I am putting some positive charges. So there are electric fluxes coming inside, right? So this electric flux, let's say this is D, your displacement vector. So we know that this displacement vector is nothing but epsilon times electric field, right? And this is nothing but the total charge, right? So if I have positive, because this is my insulator here, this is my insulator. So if I have certain positive charges in the gate, I'll have the same amount of charges on the other side, right? Other side we have silicon, right? So this epsilon E is also equal to the silicon, and this should be minus because if I am applying positive charge in the gate, so other charge will be negative, right, in the silicon charge side. And I could also write this as epsilon Si times Es, right? So if you want to write the silicon charge, right, the silicon charge is nothing but what is the field at the interface. That field is yours Es, right? That is the field entering, because means you could think of this as a closed um, box or something. So the electric field at the surface of this box, right? So this is your Es, right? So total charge enclosed in this part is Q silicon. So if you Q silicon, you could easily find which is epsilon silicon times the field at the surface, right? And this is the silicon field, right? Please, right? This might the silicon field, right? So, but the oxide field will be different. Oxide field will be silicon field. Um, sorry, epsilon silicon divided by epsilon, right? Okay, so so if you want to find the Q silicon, right? So in this here I have find this field at the surface of silicon, right? So this is basically, I could write this is actually silicon, the surface of silicon, right? So then I could find Q's silicon is nothing but your um, the electric field at the surface times epsilon silicon, right? Right. So then I could, means if I do that, so I'll have this equation, right? So I have this equation, right? So this is actually the total charge, right? So this is the universal equation. Why universal equation? Because this equation is valid for any value of psi s, right? The psi s can be negative. We discussed in the last class. When you're operating the accumulation, that means when you're applying negative gate voltage, your psi s is negative. When you're applying positive gate voltage, your psi s is positive, right? So across, so this is a universal equation. The charge in the silicon is a function of psi s like this, right? So this is the equation. This is the charge in the silicon and the potential drop across the silicon. This is the relation between charge and the potential drop across silicon, right? So if so, basically in the flat band condition means when there is flat, the condition MOS transistor, the condition where the total charge is zero, right? So that means the bands are flat, energy bands are flat. That means yours there is no potential, so potential drop in the silicon. So if psi s is zero, if you put psi s equal 0, your Q silicon will be zero. So no charge means there is no potential. So there is no net charge. So there is no potential at the potential drop in the silicon. Right. When I talk about accumulation condition, right? Accumulation, that means your psi s is negative. In the accumulation, you are applying negative gate voltage. Your drop in the means basically psi s is nothing but your potential drop in the silicon, right? And the psi s is negative. That means your Q psi s is negative and your Q psi s by kt is also greater than 1. Because see, your kt by q, if because kt by q is around 26 millivolt, right? So when you are going deep into the accumulation, right, that means your q psi s by kt mod of that, because this is a negative number, q mod of that is much higher than 1, right? So basically what I'm telling is your psi s is much higher than kt by q, right? If this is the condition, in this condition, right, accumulation condition, so your if you so basically you see your psi s is negative. If your psi s is negative, right, so then this part will be positive because this is e to the power minus q psi s by kt. This part will be positive, this part will be negative, right? So so you see e to the q psi s by kt, this will be this number here. So this here will be much higher than other parts, right? So and please keep in mind um, this one here, sorry, this part here, right? So this part is almost, you see, this is 10 to the 20. If your doping is 10 to the 34, let's say 10 to the 17 Na, so this is almost 10 to the minus 14, right? So this is a very small number, right? Ni square by Na square is a very small number, right? So if your q, if this term is positive, this term is negative, so this, so basically you could see that this term will be very small because this is a negative number, means, right? So not negative actually, sorry, right? So q psi s by kt is negative, right? Q psi s by kt is negative. So e to the power minus e to the power a negative number, right? So e to the power a negative number, this will be very small, right? So this is very small, right? And there is, so this will be positive, right? So this will also be, this will be positive, right? But it is multiplied by 10 to the minus 14, right? So this will be a very small number. So your silicon means your q silicon, you could approximate as only root over 2 epsilon NAKT root over into e to the minus q psi s by 2 kt, right? So this is my accumulation charge, right? So this is the charge in the silicon in the accumulation charge, right? Right? You see, in the accumulation, when the transistor in the accumulation, so your charge in the silicon is exponentially dependent on your potential drop across silicon, right? Psi s is the potential drop in the silicon, right? So it's an exponential dependence. Since the psi s is negative, so your as the psi s increases, psi s becomes more and more negative. your charge in the accumulation will also increase, right? Right, and that is exponential dependence, right? Okay. Now, when psi s is positive, right? So when psi s is positive, psi s will be positive because when I apply positive get voltage, right? So this will be the condition when the gate voltage is positive, right? So when the gate voltage is positive, your psi s is positive also, right? So your q psi s by kt will be more than 1 because definitely your psi s is more than 26 millivolts. So your q psi s by kt is more than 1. And if I look at this equation again, so this equation here, so here this term, this is you see this is a negative, this will be a small, right? This will be small, right? Um, but this term is not small, right? This term is not small. This is q psi s by kt. So let's say psi s, if the psi s is 100 millivolt, so this will be 100 millivolt by 26 millivolt around 4, right? So basically this will be 4 minus 1 3, right? Anyway, so and if you look at, and this number is 10 to the minus 14 here, right? In this case, and if you look at this number e to the q psi s by kt, right? So this is a large number, right? This is a large number because it is, if psi s equal 100 more, this is e to the power 4, right? So compared to this number, um, so here you could write down e to the power q psi s by kt will be definitely more than q psi s by kt, right? Q psi s by kt plus 1. Sorry. Q psi s by kt plus 1. So when the psi s is positive, you could neglect these two numbers, right? You could neglect this number, right? And so here you could write down. So from this part, I'll have q psi s by kt from here, right? This one, right? And then from the second term, I'll have only e to the power q psi s by kt. So I'll have this term, right? So your silicon charge is the summation of these two terms, right? And if you see, if you little bit modify, right? So I'll have this first term. This is term 1, right? So this is root over 2 epsilon qna into root over psi s, right? And if you look at the second term, so this is a exponential term, right? So this is term 2. So term 2 has a exponential psi s dependence, and term 1 has a root over psi s dependence, right? So if you look, and we have already discussed, right? So if you see your depletion charge, right, is nothing but q times na times wd, right? And we know that wd has a root over dependence, right? So your qd is proportional to root over psi s. So let me find out that yeah, here, right? So it did that, right? So your wd is this we had derived, right? So if you go back, um, so you see this is your wd. So I could also write down this as q times na root over 2 epsilon si q na psi s. So this is nothing but 2 epsilon si q na root over psi s, right? Right. So this equation we already know. This is the total depletion charge, and this is nothing the same, right? So this term 1 is nothing but the depletion charge, right? Right. If the term 1 is the depletion charge, right? So your total, so when Vg is positive, your silicon charge is nothing but depletion charge plus inversion charge, because there will be some number of electrons also, because you have, the moment you deplete the silicon, right? So there are immobile charges, and that increases potential. So electrons start coming from source and drain, right? So total charge in the silicon is nothing but depletion charge plus inversion charge or inversion charge. So the second term will be the inversion charge, right? So second term is the inversion charge. So you see the depletion charge is proportional to root over psi s, but the inversion charge, the number of electrons is proportional to proportional to exponential of psi s, right? So this is my inversion charge. So uh, so your Q silicon is QD plus Q inversion, and QD is root over 2 epsilon Si QNA times root over psi s. So this is some constant because let's say K1 times root over psi s. So you see, and right, so your inversion charge um, root over 2 epsilon Si Na times Kt Ni by Na, or I could take it inside, right? Ni square Kt Na, it is by Q psi s by 2 Kt. Right. So if you look at the look at this term, this is also constant because once the transistor is fabricated, this is also constant. So this is K2 times e to the power Q psi s by 2 Kt. Right. Okay. So so this is my depletion charge. This is my depletion charge, root over psi s dependence, inversion charge, exponential psi s dependence. Right. So and also we also saw your accumulation charge also exponential psi s dependence. So again your accumulation charge I could also write Q in the accumulation is equal to nothing but some constant e to the minus Q psi s by 2 Kt. Right. So now if I plot that how this the charge in the silicon. So this is my silicon charge, right? Charge in the silicon, and this is the potential drop across silicon psi s, right? So how does it vary? So you see in the accumulation, so if psi s is negative, that means this is accumulation, right? So this part is accumulation, psi s is negative. So here your charge varies exponentially, right? And this has an exponential dependence, right? Your charge varies exponentially, right? And when the psi s is positive, so we have two terms. One is exponential dependence, right? So you have exponential dependence. So this is log plot. So you have exponential dependence. So here I'll just draw it. So you have exponential dependence, and another one is a psi s dependence, right? So you are just adding these two, right? So when psi s is very small, when psi s is very small, when the surface potential is very small, so you think of your transistor, right? So this is psi s here, the potential at the surface, right? When the psi s is very small, so that means these two junctions are less forward biased, right? Those junctions less forward biased, so we have less number of electrons. But there are depletion charge, right? As you go on increasing psi s, your number of electrons are increasing exponentially. So you will have an exponential number of inversion charge increases exponentially, and your depletion charge also increases because as you increasing your gate voltage, your depletion charge increases. That's the reason your psi s increases, right? So your depletion charge increases, but depletion charge is increasing root over psi s, right? And but your inversion charge is increasing exponentially, right? At some point, right, your inversion charge will be more than the depletion charge, right? And that point is mostly it is around 2 psi b, right? Little bit more than 2 psi b. So this is the 2 psi b that we have discussed yesterday, right? 2 psi b is nothing but 2 kt by q ln na by ni, right? So okay, and so this part we have we call the depletion, right? And weak inversion, right? So weak inversion. So see, basically Even if your, so as I told you in the last class, right? Let's say psi s is very small. Let's say psi s is only 100 millivolt, right? Right? So psi s equal to 100 millivolt. That means these two junctions are forward biased by 100 millivolt, right? So there will be some injection of electrons from source and drain to the substrate, right? And these electrons will accumulate here, right? So even if your psi s is very small, it is much smaller than the depletion charge. But the moment your psi s becomes positive, there are electrons in the channel, right? There are electrons in the substrate, this region, right? There are electrons, right? But this number of electrons are very small, right? And now much smaller than the depletion charge, right? So as you go on increasing psi s, at some point of time, there will be enough number of electrons, even if they are smaller than depletion charge, but they are comparable to the depletion charge, right? So that part we call weak inversion, right? So they are okay. We have electrons, but this is weak inversion because those number of electrons are compared to the depletion charge, but not more than the depletion charge, right? After some point here, this is the weak inversion. So strong inversion is where the number of electrons is much higher than the depletion charge. So the total, so in this case, right? So in this part, your QSI will be Q inversion, right? When the strong inversion part, your total silicon charge is nothing but your inversion charge, because depletion charge is much smaller than your depletion charge is much smaller than the inversion charge, right? Right? That is in the strong inversion. In the weak inversion, your QD and Q inversion are comparable, right? So your Q inversion is increasing, your QD is increasing slowly, but Q inversion is increasing very fast. But in the weak inversion region, your Q inversion is not more than QD, but they are comparable. They are very almost close to the Q depletion, right? But in the depletion region, that means you have, so in this part, so we call it depletion. We call it depletion, but there are electrons, right? That means this region is not fully depleted of carriers, right? There are electrons, but the number of electrons are very small, right? Much smaller than your depletion charge. So we just neglect it, right? So this is, so here if you assume that this is where we are taking depletion approximation, right? So you are taking depletion approximation, the number of electrons are much smaller than the depletion charge. Okay, so this is the typical means this is the the charts, your QSI and psi s, right? So this is the charge in the silicon and the potential across the silicon, right? But but outside, I am not applying psi s, right? So I need a relation between, because I need a relation between QSI and VG, right? Because the voltage that I'm applying is gate voltage. I'm not applying surface potential. I'm not applying psi s, right? I am applying VG. So this plot only gives a relation between charge in the silicon and potential in the silicon, right? But I want charge in the silicon as a function of voltage applied. Applied voltage is gate voltage, right? So if I want to do that, so basically, I mean, we have done it. So your gate voltage is nothing but your potential drop across the oxide plus your silicon, right? Your potential drop across silicon, right? So this is I mean, I could do it quickly, but we had already done that, right? So assuming there are no charges in the oxide, so you could write down this is uh, um, right. So here I could also write down this as because you could write down slim side um, by epsilon ox into Tox plus Is, and this is nothing but sun silicon epsilon ox, sorry, Cox plus Is, right? And that is your relationship, right? Relationship is QSI by Cox plus Is, right? This is how your gate voltage is related to Is, right? But again, your QSI here is a function of Is, right? So so if I look at uh, only the depletion charge, right? So let's say if my psi s is much less than 2 psi b, right? If a psi s is much less than 2 psi b, right? That means, right? So that means it's in depletion condition. So your Vg will be 1 by Cox, right? So we wrote the depletion charge, which is root of 2si, right? So this is nothing but some constant times root over psi s plus psi s, right? So this is an equation that if you want to, because we want, see what we want, right? So for the terminal characteristic, if you want to find the IV, means current voltage terminal characteristic, so basically what you want a relation between QSI and VG, gate voltage, because this is the voltage you are applying, right? But we know how QSI as a function of psi s, we know, right? So then we have to find psi s as a function of Vg, right? So basically, if we have applied gate voltage here, some gate voltage, then you will find what is the psi s, right? If you know psi s, then you put it here, then you'll find QSI. Then you will have a relation between QSI and Vg, right? So this is the relation between, so this equation just tells you the relation between psi s and means potential drop across silicon and gate voltage. So you have to solve this. This is not a very straightforward equation. So this is a transcendental equation, and mainly you have to, if you want to have a relation, then you have to solve it numerically. You could only numerically solve it, right? So you apply some Vg, then you find what should be that psi s, and that could only be solved numerically. Okay, so now if I write down the equation again, so Vg, so this gate voltage is QSI by Cox plus psi s. But if your psi s is much higher than 2 phi b, right? So that means much higher than 2 kt by q ln Na by Ni. That means your inversion charge. So in this condition, your inversion charge is higher than the depletion charge. So your gate voltage is nothing but your inversion charge divided by Cox plus 2 psi b or psi s, right? Right. So here you see. So what is this one is your Vx, right? So if I write down that again, so 1 by Cox, right? So Q inversion. Uh, okay, all right. Okay, so this will be the equation, right? So Vg will be this term plus this term, right? So here you see, if I'm increasing, so so anyway, your psi s is more than 2 psi b, right? Psi s is more than 2 psi b. If psi s is more than 2 psi b, I could write this equation because I have neglected the depletion charge, right? So now in this condition, if I give some delta Vg, let's say I have at this Vg, my psi s equal to I give some delta here, right? I give some delta here, right? So let's say I give some delta Vg here, right? Right. See, this delta Vg will increase psi s, right? So this delta Vg will increase the surface potential. So if I increase gate voltage, my surface potential will also increase. So if my surface potential has a delta, so that means this will be psi plus psi s plus delta, and this is also psi s plus delta. So if you see, and I am giving some delta Vg here, so this is delta psi s and delta psi s, right? Right. So you see, if I give a delta Vg here, so I am increasing delta psi s, but if you look at these two terms, right? So this has exponential dependent delta psi s, this has a linear dependent delta psi s. So this term will increase very high, right? Right. So this is my Vx, right? What I'm telling here is once the device is in inversion, if I give certain change in gate voltage, right? So I'll change some gate voltage, and so the Vx, your oxide voltage, will increase very fast compared to the drop in the silicon. So you think of this, right? So I am giving some Vg, right? So I have some drop in oxide and rest I'm getting in the silicon, right? So Vg equal to Vx plus psi s, right? If this, I mean, if my transistor is inversion, if I'm giving delta Vg here, some additional voltage, so by Kirchhoff's voltage law, so this delta Vg will drop across Vx across psi s, right? So, right. So I'll have a delta Vx plus delta psi s, right? What I'm telling here is once the device is inversion, so if I'm giving a delta Vg here, so most of this delta Vg will drop across delta Vx, means drop across oxide, right? Because your oxide voltage is increasing exponentially with psi s, right? But your, right? So out of delta Vg, right? Delta Vg will be almost equal to delta Vx, and your delta psi s will be very less. Right? So in the inversion, so once your transistor is in inversion, so any change in gate voltage, right? Any change in gate voltage, so that voltage will drop across oxide. So that will not be transferred to the surface, so means to the silicon, right? So, if I want to now, if I want to draw Vg, means if I want to draw Vg and psi s, right? Let's say this is your Vg, and this is uh, this is a surface potential. So let's say this is one line, right? Vg equal to psi s line. So this line is Vg equal to psi s, right? So if you look at this equation, when the psi s Vg is small, so that means your transistor is in inversion. Sorry, the transistor is in depletion. So in the depletion part, your Vg equal to C1 root over psi s plus psi s. So definitely your Vg is not equal to psi s, right? So your psi, right? So your psi s is less than Vg. So you will have something like this, right? So this will increase, but this will increase at a lower stop, right? So Vg psi s will be like this, right? So see this equation you could get by solving numerically, right? So I'm just doing it from the intuition, right? Intuition in the sense, right? I know this equation Vg equal to some constant root over psi s plus psi s. So that means this will be definitely your psi s will be less than Vg, right? So right, so this will happen, right? So it will increase, right? And the moment your Vg, your psi s becomes 2 psi b, that means your surface inverted. So after that, right, as you go on increasing Vg, your psi s will not in your psi will saturate, right? Right. So this is the inversion part, right? So this is my depletion region. So this region is depletion, right? Depletion plus weak inversion, and this region is strong inversion, right? Once the transfer in the strong inversion, so your gate voltage, right? If you increase gate voltage in the strong inversion, your charge in your potential drop in the silicon will not change, right? So basically, after inversion, your potential in the silicon remains almost constant. So the extra Vg that you're applying here, right? Extra Vg. So most of this gate voltage will drop across oxide, right? Right. So and if you plot, this is psi s. This is psi s Vg. So you could also plot the oxide voltage. Oxide voltage is nothing but if you reduce, means Vg minus psi s will be your oxide voltage drop, right? Voltage drop at oxide, right? So basically, after inversion, you will have a lot of voltage drop in the oxide, right? So that's the reason, means your field across your oxide, your gate dielectric increases exponentially I mean, increases very strongly after after inversion. Right. So this is the psi s versus Bg. So what you saw here is we saw the Qs versus psi s. Then we know psi s versus Bg. So now we could, combining these two plots, I could have Bg and QSI, right? Right. Okay. So any doubt here? Any doubt? No doubts. It's really good if you understand everything. Um, Sarda?
No, sir. Actually, I have to go through it once again. But up till now, yes, I understood things.
Aditya?
Sir.
No questions?
Sir, I have a question.
Yeah.
Sir, I understand uh, everything till now, but I am just wondering, like, what is happening after 2 Saibi, that why all the, like, physically what is happening, that all the voltage drop is only going to upside.
It's a very good question, right? So, what is actually happening is okay. Uh, right. So let's put your source and drain to 0, and your body is at ground, and you're applying gate voltage, right? So you're applying gate voltage more than threshold voltage. That means your gate voltage is more than threshold voltage. That means inversion, right? Um, so what happens that when your gate voltage is around threshold voltage, a little bit more than threshold voltage, so you have a inversion, you have lot of electrons at the surface, right? So this is the inversion charge or the inversion layer, right? Or so you have a channel formation, right? So you have lot of electrons because see um, um, you have, so what happens is you have electric field in this direction, right, from gate to substrate, and you have electron injection from both the from source and drain to the body, and these electrons, because of the electric field, so they go and accumulate at the surface and form a inversion layer, right? So there is an inversion layer, right? So this is the inversion layer with some finite thickness, and this thickness is very small actually because of the electric field. So the electrons are right at the surface, right? So very closely, because lot of electrons sitting there at the surface, right? So if we have lot of charge at the surface, right? So if you apply, so what will happen if you apply gate voltage, right? If you apply gate voltage, that means you're putting more charges here. That means you are increasing the electric field. But since we have lot of electrons sitting at the surface, this electric field will not penetrate. Means electric field cannot penetrate to the body, right? Because I have a sheet of charge sitting there, right? Very high concentration charge, right? So electric field cannot penetrate, right? Right? If the electric field cannot penetrate, your depletion charge is not changing much, right? If the depletion charge uh, is not changing, so there is not much change in the potential. But the point is, after inversion, when Vg is greater than Vts, little bit change in Vg, right? Even if there is a small change in psi s, even if there is a small change in surface in the drop factor silicon, right? So that small change increases the number of electrons exponentially, right? So if you see here, so after inversion, your number of electrons increase exponentially, right? So if the number of electrons increases exponentially, so in after inversion, your means again this plot is good actually. So after inversion, your charge in the silicon, your QSI is increasing exponentially, right? And your voltage drop across oxide, your Vox, right? Your Vox is nothing but your charge by Cox, right? Right? So since your charge is increasing exponential after inversion, charge in the silicon, So your Vx will increase rapidly, right? So since Vx is increasing rapidly and your Vg you are increasing, and Vx is means mostly, let's say Vg you increase by amount delta. So that means out of that delta, 90% of this delta will drop across oxide, because oxide increase, oxide voltage drop across, because your charge is increasing exponentially. So voltage drop in the oxide will increase. So 90% of those drop in the oxide and 10% will only drops in the silicon. Right? That's the reason your after inversion, your in, the potential drop in the silicon, almost if you measure the what is the potential drop in the silicon and what is the potential drop in the oxide, right? So your potential drop in the silicon almost remains constant, right? So there is a slight increase. So when I'm telling that this part here, right? So this has a finite slope, right? So this has a finite slope. It's not like that it's remaining constant. This has a finite slope, right? But this is very slowly increasing. Your surface potential is very slowly increasing. Even so, that is my point, right? Even if your surface potential is very slowly increasing, that has an exponential impact on the charge. And since the charge is exponentially dependent on psi s is increasing very slowly, and but your Vx will increase. So this is because one case, first thing, your electric field is not penetrating the silicon, so depletion charge is not changing at all, right? Because so your most of the electric field means uh, terminates on the number of electrons at the surface, right? So you could think of, we have a lot of charge at the surface, so electric fields cannot penetrate, right? So if the electric fields cannot penetrate, that means your depletion charge is not increasing, right? And so what is increasing in the inversion is your number of electrons that increases exponentially. Since that increases exponentially, so your oxide voltage drop also increases very fast. So your so that has a means you could tell this has a feedback effect. So that does not allow your psi s to increase faster. So
Yes,
is
sir.
it clear, Om? Am I clear?
Yes, sir. Yes, sir. It is clear.
Okay. So um, so if I now write down this equation, right, I know that Vg equal to Q Si by Cox plus your psi s, right? So I have Qd plus Q inversion by Cox plus psi s, right? So if I want to define threshold voltage, right? So threshold voltage, right? So I told you threshold voltage is the gate voltage where the number of electrons at the surface becomes Na, right? So doping of the substrate, right? So if I, so basically, see when you're looking, okay, let me write. So this is Qd by Cox plus Q inversion divided by Cox plus psi s, right? So at the threshold voltage, right? When I'm talking about threshold voltage, right? So threshold voltage is the gate voltage, right? So where the psi s becomes 2 psi b, right? So psi s will be replaced by 2 psi b. But if you look at this Qd by Cox, Qd and Q inversion, right? So at because if you look at this point here, right? So at the threshold voltage, so somewhere here, right? So somewhere here, right? Your depletion, your inversion charge is just equal to depletion charge or a little bit below depletion charge, right? So what we generally do is we neglect this Q inversion, right? So what you means we just write this as VTH is QD by Cox at psi s equal to 2 psi b, right? Whatever is the depletion charge plus 2 psi b, right? So this is nothing but 1 by Cox. So QD is QD is root of 2 epsilon QNA SIS root over 2 epsilon SI QNA. So this will be root over 2 psi b plus 2 psi b, right? So right, so this is your threshold voltage. This is the equation of the threshold voltage actually, right? So this equation will use a lot. Right? So basically, if you see, if you want to find at the volt, so this is the voltage. So this part, the first term is the voltage drop. So this is the voltage drop across oxide at the threshold voltage, right? Right. So at threshold voltage, this is the voltage drop across oxide. This is the voltage drop in the silicon. Right. So voltage drop across silicon is 2 psi B. Voltage drop in the silicon, but voltage drop across oxide is rest of the voltage, right? So yeah.
Here, like QD is almost equal to Q inversion. So, like, why are we neglecting Q inversion?
Yeah. That's a good question, but see, means what I will say. So right. So actually, means it's not true because you see, you could do that, right? So you could do that exercise. So you calculate QD, right? You calculate QD from this equation at 2 psi v, and also you calculate Q inversion. So you will see that Q inversion is not equal to QD. Q inversion is smaller than QD, right? So Q inversion is so what we are telling is your number of electrons. See, um, okay, I'll explain you, right. Okay, so what I'm explaining at threshold voltage, your number of electrons at the surface, right? Surface is x equal to 0, will be equal to Na, right? So, but the depletion charge is Q times Na times Wd. This is the depletion charge, right? Right?
Yes, sir.
Your inversion charge will be Q times N0 times, your inversion charge thickness, right? So this is my Qi and this is the Qd, right? So Na equal to N0, right? So number of electrons at the surface will be equal to Na. But if you calculate the inversion charge, it will be smaller than QD, right? At that point, right? So that's the reason. You means you could calculate from the equation. You have the exact equation, so you could also calculate. So you will see that your Q inversion is not actually means it is little bit less than QD. So for the simplicity, because for the simplicity, you can see means uh, your your this part is less than QD. Q inversion by Cox is less than QD by Cox. So we just neglect Q inversion by Cox, right?
Yes, sir. Understood.
So your threshold voltage will be this equation, and this is a very universal equation. So means you could also write down this as your threshold voltage is K some constant times root over everything is constant, right? So basically you could also means your psi b is kt by q na by ni. So if you know your doping in the substrate, so you could find your threshold voltage, right? So this is the ideal case, right? In the practical case we'll come to that point, because if a transistor is not ideal, so we started with the first assumption that your metal work function is equal to semiconductor work function. If that is not the case, how the things will change, right? So that will come next, right? Okay, so this is the threshold voltage, right? So and threshold voltage, and also if you look at uh, so your vg, sorry, okay, I'll write down this equation: qd by Cox plus q inversion by Cox plus psi s. um, your threshold voltage is qd by Cox plus 2 psi b, right? Right. So when Vg is greater than Vts, that means your device is in inversion. inversion condition. So my Vg is nothing but Qd by Cox plus Q inversion by Cox plus 2 psi b, right? Right, when my device is inversion, because as I told you, right, even if you go, your gate voltage is more than threshold voltage, your psi s is mostly stays same as 2 psi b, right? It does not increase much, right? So like this equation, right? So it does not increase much, right? So I could also write this as threshold voltage because plus Q inversion by Cox, right? So if I add this term and this term, this is nothing but the threshold voltage, right? So your Q inversion, generally this is a first order equation. We write Cox Vg minus Vth, right? So this equation we very fondly use many places if you want to find the number of electrons in the inversion, because Q inversion is nothing but your electrons only, right? Because as I told you, your total charge is Q depletion plus Q inversion, right? But in the inversion condition, if you see here, inversion condition, total your QD, if you go deep in inversion, very strong inversion, right? So your QD is much smaller than Q inversion. So in that case, you could write this as Q inversion. So your inversion, if you want, you only find the inversions, because see, because this inversion charge is mobile. So this charge is only mobile charge, right? So we don't care about QD, because QD, even if you apply some 10 voltage, QD will not move. Your inversion charge will move, right? So for the current equation, we need this inversion charge, right? So this is a simple formula to calculate the inversion charge. This is not an exact formula, but a very simple and okay time, like it will not give you very wrong values. So Q inversion is nothing but your Cox times Vgs minus Vt, right? So and this is nothing but Cox, we call it overdrive voltage, right? So Vgs minus Vth is the overdrive voltage, but whatever is the we give above Vt, right? Overdrive voltage of the transistor. Okay, so this is the inversion charge. And another thing which is very important is your inversion thickness, right? Because because your, if you see, um, again, if I draw, so I have depletion charges. I have my depletion charges, right? So and I have a and then I have my channel, which is means electrons which are accumulated at the surface in the strong inversion, right? So when I'm talking about strong inversion, right? So this is Vg greater than Vth, right? So as I told you, since the so moment your surface inverts, moment we enter strong inversion, so electric fields are not penetrating because you have a lot of electrons sitting at the surface. So this just blocks, this just seals the electric field, right? So electric field is not penetrating, so your depletion charge will not change, right? So your depletion width will almost be almost fixed, right? So we call it the maximum depletion width, right? So the maximum depletion width will be so we have written this WD का equation लिखा था ना हमने. Okay, just a minute. Yeah, this equation here. So this is your equation of WD, right? So this is the equation of WD, but after inversion, your depletion width is fixed, right? So and that is the maximum WD max, right? Maximum depletion width is 2 epsilon Si QNA times 2 psi b. Right, so this is the maximum depletion width, right? Because means once the surface inverts, once you have a lot of electrons at the surface, your electric field cannot penetrate, so your depletion charge will not change, right? So you have a maximum depletion width, right? So this is WD max, right? So it Vg greater than Vth, your depletion would still be Wt max, right? And this is the equation. But also this is the inversion. We have electrons and we means inversion layer, and inversion layer has a finite thickness. But this Ti will change as you go on increasing your gate voltage, right? Because as you change in your gate voltage, your electric field is increasing. So if your electric field is increasing, so your electrons will move more and more closer to the surface, right? So your inversion layer thickness, your Ti will reduce with Vg. That means your Ti will reduce with depletion charge, right? As you increase, if you increase Q inversion, that means you are increasing gate voltage, you are increasing Q inversion, you are increasing electric field. That means your electrons are means moving more and more close to the surface, and they are becoming compact, right? So basically, a lot of electric field. So everybody is pulled, right? All the electrons are pulled to the top, right? So your inversion layer thickness reduces with increase in gate voltage, right? And how does it happen? So if you look at this equation, right? So if you look at this equation, Q inversion, we have derived this equation. So this Q inversion, I could also write that Qn0. Qn0 means N0 is the number of electrons at the surface, right? Q times N0 is the charge, total charge is Ti, right? So you keep in mind, right? So this is unit is per centimeter square, right? Q inversion. This unit is per centimeter cube. When I'm telling that n number of electrons becomes equal to doping, that means this is per centimeter cube, and this is centimeter, right? So if I multiply per centimeter cube into centimeter, this will be per area, right? Right. So if I write Ti, right, from this equation, I could write this Ti equal to Q inversion by Qn0. And the number of electrons at the surface, I know this is my equation. This is very standard equation, right? And we have also seen in the junctions in bipolar junction transistor everywhere, right? The number of electrons equal to Ni square by Na is the number of electrons when not applying any potential across the junction times e to the power q psi s by kt, right? So then Ti, I'll just divide these two, right? If I divide these two, do math, so your Ti will be means will be this one, right? So I will not go. So here you see your inversion layer thickness is proportional to the inversion charge, right? As you go on increasing the inversion charge, your inversion layer thickness will reduce, right? So that means your volume means basically, if you look at how many electrons are actually being concentrated at the surface, right? So if your Q inversion is very low, right? So let's say you are not operating the depletion region, right? You are not operating in the depletion region. You are not operating in the inversion region. So your Vg is very low, right? Let's say Vg equal to 100 millivolt, which is less than threshold voltage. That means you have electrons, but electrons are roaming around. Electrons are somewhere here, right? They are not actually at the surface, right? So they are somewhere in the depletion region, right? But as you go on increasing your gate voltage, right? So electric field is increasing, and electrons are slowly pulled to the surface, and they get accumulated at the surface, right? And now if you're increasing electric field more and more, right? If you're increasing electric field more and more, so your inversion layer thickness reduces, right? So okay, so this is the inversion thickness Ti. If you want to find, if you know Q inversion, you could find the T inversion also. Okay, so I think I only have this part. Okay, so I think we should stop here today. Any questions